I won't take up much of your time today. On your second worksheet, I just wanted to go over number 10 because had we had the opportunity, we would discuss this at some point, and that is you're going to have to decide, am I a dimensional analysis person or am I an ideal gas law person? So in this case, sometimes if a gas is at STP, you don't necessarily have to use the ideal gas law. That works every time, okay? Because if you are an ideal gas law person, that's fine because we know what our pressure is and we know what our temperature is because it's being measured at STP. But like for instance in number 10, since it's measured at STP and you're looking for a mass, if you want to just use dimensional analysis, you can do that. But one of the things to be careful of, yes, you do need to decide, am I an ideal gas law person when we see this, or am I a dimensional analysis? And even if you do use the ideal gas law, there's just one step of dimensional analysis that goes with that. And one of the reasons that we say that is we were introduced to something similar to that when it came to percent composition of compounds. Yes, there was a shortcut that you could take to go through that, but one of the things we had said, I highly recommend that we don't teach that, but some students may have found, well, this is much easier. But when you keep things consistent, it will work a lot easier for you. So again, this is number 10 on your second paper. It says, what is the mass in grams of 3.40 cubic centimeters of F3 at STP? So one of the things that you can do is, if you're going to say, I'm an ideal gas law person, okay, there's nothing wrong with that, okay, because one of the things we'd say, you know the pressure is 1 atmosphere because, again, it's at STP, okay. We know the volume, it's 3.40 milliliters because that's what a cubic centimeter is. So you're going to want to divide that by 1,000 to give you 0.00340 liters now, okay? And we're just not making these variables up because remember the ideal gas law was this. Oops, almost forgot about the N. Okay, that's your pressure times your volume equals the number of moles times the constant times temperature, okay? So then what is our N value? Well, we don't know, okay? R is a given, 0.0821, and of course temperature is 273, okay? And if we take certain liberties to this, since this is on the right side of your equation, to get the R value, we would take the volume of 22.4 and divide that by 273, and then that gives you 0.0821. So you know enough about with your algebraic skills to undo division would be multiplication. So if you were to multiply these two, 273 times 0.0821, and of course that's going to give you 22.41. So for every mole of a gas, okay, at STP there are 22.4 liters. Okay, so if you just want to use straight up dimensional analysis, that works because it's measured at STP. But your ideal gas law, that will always work. Okay, so what do we mean by that? Well, if we put this together where everything belongs, we know anything times 1 is just going to give you the same number. So 0.003, I meant to use a different color marker. Let me start over with that. Okay. 0.00340 times 1 just gives you the same number. And if you're more comfortable with writing these out, that's no problem. 0.0821 times 273 times N. Okay, we'd already established that's 22.4. So what we're saying is 22.4 N equals, okay, 0.00340. Get N by itself, dividing each side by 22.4. Okay, and of course that's going to give you a really, really small number. In other words, 1.52 times 10 to the negative fourth, and that is moles of F3. Okay, but notice this is asking for a mass in grams. Okay, so since we are dealing with a known substance, we can take that 1.52 times 10 to the negative fourth, or if you'd rather have it as a whole number, you just move this over 4 times in 0.000152. Okay. Okay, so these two numbers are the same, but if you'd rather just leave it in scientific notation, you can do that as well. Okay, so then again, this is moles of F3. Okay, we don't need this content anymore. Go ahead and get rid of this, because again, the question is asking for the amount in grams. So it's a known substance. How do we get rid of our mole? Well, we put moles of F3 on the bottom. Then for every atom of fluorine, I believe, isn't it 19, I think? Yes. So 19 times 3, what's that, 57? Yes. You have 57 grams of F3. Okay, so once upon doing that, you would take 1.52, and then if you have a Texas Instruments, what is that, 35, you hit the second button and then look for the little double E's there, and that will put it in scientific notation. But if you have a graphing calculator like this, well then I believe you just look for double E, which still means I got to hit second, and then I think it's a comma there. It has 2 double E's there. 1.52 times 10 to the negative fourth, so negative 4, and then take that times 57, and that gives us 0.0087. Okay, so 0.0087. Okay, and that's grams of F3. Okay, so the ideal gas law is one that will always work, but if you feel more comfortable with just straight up dimensional analysis, you can do that as well. Okay, so in order to do that, we have to have a place to start, and that is, let's see here, I'll just keep this as a purple color, 3.40 cubic centimeters, or if you do this in dimensional analysis, you have to have it in liters, so 0.00340 liters of F3. Okay, we know that for every mole of a gas at STP, there's 22.4 liters of that. So in order to do this, we need liters of F3 to cancel. We know that for every 22.4 liters of F3, you're going to get a mole of F3. Well, how do we know this? This is why, because it's measured at STP. Now we're in moles. We can cancel out our mole here and then put 57 grams of F3. Okay, so when we used the ideal gas law, we got to this point and we had to do just a two-step problem to get the answer that we're looking for. But if it's measured at STP and you just want to use dimensional analysis, that's fine too. Let's see what we get for an answer. If we take 0.00340 times 57, hit enter, gives us 0.1938, but we got to divide by 22.4 yet. That gives us an answer of 0.0087. Okay? 0.0087, okay, grams of F3. Okay? Two different ways to get the same answer. Okay? Some of you just may decide, I'm just always going to use the ideal gas law because I know that it works. But look at this, it's a little shorter. You can take this and use this dimensional analysis only when gases are measured at STP though. All right, so I wanted to keep this short just to give you somewhat of an idea on where we were at. So as far as papers are concerned, at the end of class tomorrow, should we be in session, have the first paper done, and that's just says molar gas volumes on top. Okay, then worksheet 2 is the one that says, I think, something about molar mass and ideal gas law. That's worksheet 2. That will be due on Monday. Okay, that's if we are in class tomorrow. If we don't have school, well then worksheet 1, the one that says molar gas volumes, will be due on Monday, and then the molar mass and ideal gas law paper, worksheet 2, will be due on Tuesday. Okay, so I'm going to write this down as well, so hopefully we're on the same page and try to get through this content. Okay, thanks for tuning in, and hopefully you found this useful, and we will catch up to you next time.